introduce Rasmus TOFT-PETERSEN. And Rasmus is a senior scientist at the Technical University of Denmark. And he is also the lead scientist for the new BIFROST spectrometer that is being constructed right now at the European Spallation Source in Lund. Before Rasmus joined the ESS, he worked as an instrument scientist at the cold triple axis spectrometer FLEXX, which many of you may know and doesn't exist anymore, unfortunately, at the Helmholtz Center in Berlin. And as a scientist there, he started to work on the concept of multiplexing backends. And today he will give kind of a chronological overview of the different implementations of these concepts. And before we start some technicalities, you will have the possibility to ask questions. Also, there will be a small break halfway through the talk where you will be able to ask questions. And with either the question and answer icon at your task at the screen, or by the raise hand feature, which you find when you go in the panelist icon. Yeah. Okay, Rasmus, the stage is yours now.
Thanks a lot, Christoph. I'll just jump right in. So just a brief outline of what I'll be discussing today is I'll try to motivate why we do multiplexing at all. And that very much taps into the complementarity between a triple axis spectrometer and a time-of-flight spectrometer in cold spectroscopy. Before going into all these different analyzer designs, I'd like to briefly go through some of the analyzer basics. And then I'll just discuss some of the early setups, Rita and Puma and flat cone, that most of you might know. And I'll quickly move on to discuss the transparency setups, where you use the transparency of graphite, for instance, to increase performance even more. And those are MultiFLEXX and Bambus. And then there are complex versions of this, and that's the recently built CAMEA spectrometer at the PSI. And BIFROST is very much an inspiration, inspired by CAMEA, because the back end is the same, but there's of course central differences in the front end where we employ an indirect geometry, time-of-flight front end, and I'm going to explain what the advantages of that is, and end with some concluding remarks. So moving on, I'm just going to do this, move this a little bit away. So moving on, so cold neutron spectroscopy is in the low energy regime, of course. So we look at low energy phenomena like phonons, mostly magnetic excitations like spin waves and spin-ons, sometimes also crystal fields, but the energy scale is between roughly 0.1 MeV and 10 MeV. Okay, I'm trying to. There we are. And we, of course, do this by either measuring or preparing an incident wave vector of the neutron, and we measure or prepare a final wave vector, or scattered wave vector of the neutron. And then we have a scattering triangle, and then we use that to determine, to measure the excitations. And a triple axis spectrometer is the workhorse tool, has been for a long time. And that's based on using crystals for monochromatizing your beams. So we use the relationship between the takeoff angle on the crystal of the neutrons, the reciprocal lattice vector that you're using for monochromatizing your beam, and then that gives you a relationship defining your scattered wave vector. And then you place your sample in a scattering condition, and that gives you an incident wave vector. And you play the exact same trick on the back end, where you have a shielded construction housing and possibly a collimator, but an analyzer and a detector system that is is rotatable around the sample position, and the detector is rotatable around the analyzer. And in that way, you can prepare your final wave vector as you please, and in a scattering angle as you please, and that gives you a scattering triangle. And you can use that, of course, to measure the momentum transfer and the energy transfer of the scattering process, and that gives you information of the system that you are measuring. Multiplexing works by, we're not trying to multiplex the incident energy. That's too hard. I don't think it's possible. But we do it by multiplexing the scattered neutron energy. So we want to build an ensemble of analyzers and detectors, of course shielded, that is able to probe more than one scattering angle at the same time, and sometimes also more than one scattered energy at the same time. And that's a way of drastically improving the performance of these machines. So just to put things in a historical perspective, the triple axis spectrometer, the workhorse of cold neutron spectroscopy, at least in the early days, was invented in the mid-50s. And back then there was a lot to do, of course. You could do all the low-hanging fruits like magnons and terbium and all the highly scattering systems or the strong scatterers. But in 1986, the high TC superconductors were discovered. And those are, as a starting point, the parent systems are magnetic, and the systems are also, the magnetic excitations are likely the drivers of the superconducting state. And then, the scattering, the moment of these magnetic excitations is very small. So the moment is small in these systems. And these systems also spurred interest in quantum phase transitions. And that also spurred interest in new quantum states like spin liquids. So there's a development towards the more complex and the low spin systems. From a instrumental point of view, we have always had the triple axis spectrometer, at least since '55. But recently, the time-of-flight spectrometer, of course, has emerged, and it's a very beautiful and very efficient technique if you have the samples for it. The triple axis spectrometers has also evolved by building larger monochromators. And if you curve them right and you have the right adjustable curvature, you can sacrifice only Q resolution, not energy resolution, for flux. So you increase. You make the Q resolution coarser and you gain flux in the sample. And that's a way of improving the measurement power, basically, of the instrument. And in these later years, you have these very complex multiplexing setups that works with the back end of the triple axis spectrometer to increase performance that way. And that's what we'll be discussing, of course. And also from a sample environment point of view, the thing has been getting more complex. In the mid-'80s, people started using these cryomagnets with dilution stick inserts in them, and that has been more and more used ever since. Dilution sticks are very popular. People have been starting using pressure cells and electrical fields as well, and those are small sample measurements. So there's an evolution towards more complex phenomena, frustrated systems that scatters weakly, smaller magnetic moments, smaller samples, and more complex sample environments. So the experiments are getting harder since the easy experiments has been done. And as most of you know, the flux of the sources are not evolving very fast. So two good examples of what you want to measure is for instance, this famous paper by Martin Moegal from 2013. He measured this at iron 14 at the ILL, and it was a very, very large 2 cubic centimeter crystal. So that's really on the large end of the spectrum. And he measured a spin half Heisenberg antiferromagnetic chain at 100 millikelvin. So this is with a magnet and with a dilution stick. And at 5 Tesla, the system saturates, and you're able to see these two branches for each of the sites, each of the copper sites. But at low fields or 0 field, you have this 2 and 4 spin-on continuum. And as you can see here on the plot, it's a very broad feature. So the inherent signal to noise in measuring this is, of course, lower than a sharp feature of a spin wave. So that means you have to measure something like this efficiently. And that means you need a high flux and a low background. But that's not all you would need. You also, the right-hand side gives an example of a different requirement. This is measured at LET at ISIS. That's a strong Lake Heisenberg spin half ladder. They also measured this at high fields, and you also measured this at very low temperatures with a dilution stick. And you see this very complex intertwined branches here that they wanted to measure. And you can measure this on LET because of the very good Q and energy resolution. So it's not always a good idea to sacrifice resolution for flux if you want to resolve something this complex. An additional complication is that when you use magnets, the larger field you go to, the more restricted your geometry is, because you need to fit these superconducting coils around the sample. They're very large and they restrict your geometry. They also reduce the intensity of the scattered beam because of all these aluminum rings that are here, and they serve to prevent the coils from approaching each other. And they also produce background because you have a lot of material in the beam. Here on the right-hand side, you see a simulation, a union simulation of the background from a magnet in a time-of-flight, on a time-of-flight y-axis here. I just show this to highlight that you can get some local features that resemble signals out of a magnet just by spurions. So just briefly, the two techniques that we use in cold spectroscopy, cold neutron spectroscopy, are the triple axis spectrometer and the time-of-flight spectrometer. And the triple axis spectrometer has a very high flux because it transports a large phase space onto the sample, and the average flux on reactor sources are usually higher. But the drawback is that you only measure a very small spatial angle in the single scattering plane, the horizontal one. And you also prepare both the incident and outgoing wave vector, so you measure only a single value of the energy transfer at a time. The time-of-flight machine, on the other hand, has a very low flux compared to the triple axis, 2 to 3 orders of magnitude, but you gain by being able to cover a large spatial angle around the sample because the instrument is stationary, contrary to a triple axis. And here you measure a continuous energy transfer. So the pros of a TAS are that it's the most feasible option if you have a weak signal. And if you have a magnet, it's also good because a triple axis is restricted to one horizontal scattering plane. And you have this flexible collimation, so you can adjust your Q resolution by putting simple solar collimators at various positions. But the big con of this setup is, of course, that you have no real mapping. You need to identify the regions of interest yourself, and then you only see what you go in and look for. And that's very contrary to the time-of-flight machines, where you have a large coverage in S of Q and omega. You get a full data set, 4-dimensional, and you can go look for effects you didn't expect. It's the best option. If you have a strong signal, this is the best way to measure. And you can achieve a very good resolution in Q and energy. So it's good for complex phenomena, complex dispersions. But the cons are that you have a low flux, the signals are weak, and the parametric studies are usually infeasible. It's not always the case. And spurious scattering when using magnets is something you have to deal with, but people are dealing with it, so it's not a big drawback. And another pseudo drawback is that large data sets aren't always fully analyzed. People tend to make these high symmetry cuts and analyze only that, but you actually have a lot more data. So software could go a long way in remedying that. But there is a science case, or there's a case that's not covered by any of these machines, and that's fast mapping. If you want to map a weak signal, for instance, or a high TC superconductor, something with a very low magnetic moment, that's going to be hard to do on any of these machines, but not if you multiplex. So not if you measure, you have a more efficient triple axis spectrometer where you measure these wide arrays of scattering angles and more than one scattered energy at the same time. Then you can measure these small samples. You might be able to measure pressure cells. Some of the challenging systems like the high TCs would be measured. Parametric studies is also easier to do. And if you wanted some high throughput, being able to measure one of these maps relatively quickly, you could do it as well. So just very briefly, a little bit about analyzers, because we're going to be discussing that a lot. The analyzer geometry is dependent on a lot of things. And I put graphite in here. I'll show the crystal structure of graphite because that's our preferred material in cold triple axis spectrometry because of the large reflectivity of graphite. But if you have a very well-defined geometry, so let's say this is the sample here, you have a point sample and you have a point detector, the Bragg angle is completely well-defined, and that means you only accept an infinitesimal wavelength band onto your detector in this limiting case. So that's of course useless for spectroscopy because your signal intensity will be 0. But that's never really the case in real life. In real life, you have a finite size sample and you have a finite size detector, and they're usually close enough to the analyzer for it to matter. So you accept an angular distribution now from the analyzer. So that increases the wavelength band that you're accepting in your analyzer system, analyzer detector system. But of course, you also have mosaicity. So you're not using only one delta function reciprocal lattice vector. You're using a distribution of reciprocal lattice vectors in both directions. And that means that more than one Bragg angle can be satisfied at a single point on the analyzer, and you can accept scattering from a larger portion of the analyzer, and that increases your band, your accepted bandwidth even more. And this mosaicity is, of course, something we control in designing the instrument. So the accepted wave vector distribution on the analyzer is dependent on the cotangent to the takeoff angle, so the angle here. So that is something you have to live with when you have chosen your final energy of your analyzer. That term comes in and impacts greatly your energy resolution. But you also have this, and this is the Bragg acceptance angle distribution. So this is basically the distribution of Bragg angles that is accepted by both the geometry and also the mosaicity. So those guys both come into play in this. And that's something you can adjust via collimation on a triple axis. So if you put collimators in on the right spots, you can adjust this term here and improve your resolution. So from now on, I'm just going to call this the acceptance angle. So now I'd like to talk very briefly about these pioneering designs, because they are not really doing what I set out in the introduction to do, is that they're not really increasing the raw measurement power, the overall count rate of the spectrometer, but they're increasing the flexibility. And the first design at SPINS, at NIST, and RITA at RISØ was to place, having an analyzer array, an array of analyzer blades that sit on a rotation stage, basically. This one that can rotate around its own axis, but each of the blades can also rotate around their own axis. And that gives you a lot of flexibility, both in which scattering angle you measure with this ensemble and which energy you measure with this ensemble here. And an additional flexibility comes in when you use a position-sensitive detector as well, because then you can adjust how you want to direct your scattered beams. So this is a very flexible setup. And if that's not enough, people have been contriving even more, of building even more complex setups, like the PUMA setup here, where you also translate your rotating blades. And that gives you a lot of flexibility in tailoring where you measure in SFQ and omega space. But the drawback here is that flexibility does not increase you don't increase your overall spatial angle coverage by a lot in these designs. But you do that in the flat cone design at the ILL. So what they did was that they scattered vertically upwards, basically. So you build a channel that your secondary spectrometer channel scatters vertically. So you have they have two options here: a thermal option for a final wave vector and a cold option for a final wave vector. And that's because this whole thing is movable. It can move to more than one triple axis spectrometer, and then you can adjust which one to use by the slit here. And then you have a single tube detector. And this is a relatively compact setup, so the acceptance angle of this geometry is relatively large. But the beauty of it is that you can now stack these channels side by side in an arrangement in 2 theta, allowing you to measure a very wide 2 theta array at the same time. And the flexibility of the final wave vector for thermal and cold and transportability makes this a very nice invention. And you can even tilt it out of the scattering plane, if you so please. Or what you now measure starts to resemble at least a little bit what you do on a time-of-flight machine, because now you have a predefined set of KF vectors basically in your scattering triangle, and that produces a curve in Q now that you measure. And that curve is basically fixed by this stationary setup here. You can rotate the setup around the sample, and then you can push this curve out in Q. But what you end up doing is usually rotating your sample and drags the curve around in reciprocal lattice. In the reciprocal space. And then what you do here is that you choose an incident wave vector, and then you have a predefined constant energy plane that you measure, and then you measure something like this by rotating the sample. So this is a very simple setup and very elegant. So there are some really nice pros here, is that you have a substantial gain in efficiency. You can pack in more analyzer area around the sample. The scattering angle resolution is relatively good because those crystals are relatively small compared to a triple axis analyzer. It's transportable, and the normalization is relatively simple because all channels are in principle identical. The geometry of it is identical. So single channel geometry is still suboptimal because it's not like a triple axis analyzer optimized for this measurement. It's more optimized also for stacking basically. And there's no flexibility of the backend resolution. So once you have chosen your final energy to be, for instance, in the cold regime, that's what you have to live with. So near the elastic line, you have a predestined resolution. You can't adjust EF. So I'm just going to briefly talk about MAX, even though it's a non-European instrument, because I really like the gutsiness of this design. It's a multi-axis crystal spectrometer at NIST. So what they did instead is that they multiplexed in the horizontal, and in order to fit all these channels in, they built these double bounce monochromators. So they placed two monochromators, analyzers. So they placed two analyzers in a predestined scattering condition that is then adjustable. So your final wave vector measurement is adjustable by rotating and translating these two analyzers. And that gives you some flexibility on the back end. And you can then place these analyzers side by side, a little bit like they do on the flat cone, but now you have the flexibility. A little drawback of this is that in order for this to work efficiently, apparently, you need a large mosaicity, and that increases the resolution of the backend by a bit. So on a normal triple axis at 5 MeV, the elastic line resolution is something like 180 micro EV, and on max it's something like 400, as far as I know, but that can be adjusted by collimation. One thing, of course, that should be mentioned with this design is that the monochromator, the primary spectrometer, is extremely powerful because they have a dedicated cold source and a massive monochromator. So they accept a very large divergence onto the sample. So they really sacrifice Q resolution for a raw flux. And I like the dedicatedness of this design. So you have this massive flux. You have a large spatial angle coverage in this design. It is 20 times larger, or 15 to 20 times larger than on a normal triple axis. And you have flexible and variable KF, so that's real TAS flexibility. So they have sacrificed Q resolution to get that high up in flux, and it's quite relaxed in the vertical as far as I know. And near the elastic line, the energy resolution is not what it would have been on a normal TAS for any given EF, basically. But that you can vary through collimation. But what I like about this is that it's dedicated multiplexing. The whole instrument is designed for multiplexing, so it doesn't try to have a side gig as being a TAS. So it's very gutsy design, I think. So now I'd like to move on to what I think is the most recent development, and that's the transparency setups that I would like to call them, where you when you implement the transparency of pyrolytic graphites for some wavelengths, and you can use that to have multiple KFs in the same scattering angle interval. That's the nice thing about this. So on the plot here on the right, you see Thomas Kittelman's cross-section, scattering cross-section calculation for pyrolytic graphite as a function of what I would call inverse takeoff angle. It's not the takeoff angle, it's 90 minus the takeoff angle. But you see here above 4 angstroms, you see that the only process for scattering is Bragg reflections off the 002 peaks. And that's the one you use in a triple axis with graphite. And if you're not in the Bragg condition, there's no process for scattering. So the graphite is transparent. And that's very useful because now you can place these analyzers downstream one another, behind each other, each selecting out a different final energy. And then the neutrons that doesn't fulfill the Bragg condition for the analyzer in question, that just go straight through to the next analyzer and so on. And that gives you a powerful multiplexing option in energy. The transparency has been confirmed experimentally, so it is really something that you see also when you do the measurement. So one of the first setups, as far as I know, was the one I was involved in at HZB. So we were very inspired by the flat cone, but we put 5 final energies per Q channel. So we built these cassettes here. So that was about a prefabricated cassette. They were all identical, and we put a lot of borated polyethylene in them. And then we built these small analyzers, 12 square centimeters, and they each were, satisfying the Bragg conditions for energies between 2.5 MeV and 4.5 MeV. And these cassettes were then shielded with cadmium lining on the inside, and we could then place these cassettes into this shielding arrangement here. And this whole thing, we had single tube detectors, and we had an electronics box here, and this whole thing could be dismantled and put on flex in something like 45 minutes. So it's a very powerful option to have on a triple axis, because if you want to do a mapping experiment, you can just put this on relatively quickly and do your measurement. But if you wanted to go into detail near the elastic line, you could use the triple axis option. That we thought was a very good idea. It also has a very open geometry, so the acceptance angle of this geometry is relatively open. And that has an impact on the resolution. So the MultiFLEXX resolution at any given energy is higher near the elastic line than it would have been on a triple axis. But this is something we accept, of course, because we have the triple axis still. And we have a drastic increase in analyzer area, a factor of 10. So what you then do with a machine like this, analogous to the flat cone, you measure these constant energy transfer planes. But of course, you don't measure one of them at the same time. You measure 5 of them at the same time. So that is a little bit more efficient. One little drawback of this is that the high energy transfer plane has been recorded using the low EF analyzer. And that puts a little bit of a limitation on your Q range at high energy transfers. So you don't have a choice between which EF to use for these planes. Well, you do it, but you can't do it efficiently. But that's the drawback of this. It's stationary. So that is basically what happens. We did a test of this MultiFLEXX on the PANDA spectrometer at the FRM2. That was a very successful and useful test we did, where we placed 2 of these channels in a shielding box, basically, and we did a measurement on manganese difluoride, a massive sample of manganese difluoride. And we found out a lot of issues in that test. One of them was that the geometry was a little bit too open. This 2.5 MeV analyzer was too close to the end of the shielding box, basically, and it accepted too wide or horizontal angle. And that meant we picked up a lot of air scattering, and we picked up a lot of scattering from the VTI. And in order to fix that, we built a radial collimator before the whole ensemble. Another thing is the Bragg peaks. So when you come in with an EI that is above 5 MeV, the wavelength of the Bragg peaks is below 4 angstroms, and that means you can activate these parasitic reflections here. And that happened in the prototype test when the Bragg peak came in at, for instance, 5.8 MeV. We had a lot of spurious scattering when you did a 2 theta scan of this ensemble here, sometimes hundreds of counts per second. Because of these parasitic reflections. So that means you need a filter for this to work well. You need a beryllium filter as well. Of course, as well, if you don't have a beryllium filter, you can also not use EIs above 10 MeV. Start to become a problem because you activate second order reflections of 2.5, 3, and 3.5, 4, and 4.5. So you can activate those as well. So that gives you, of course, peaks at high energy transfers. When we had a filter, the instrument worked very well, I must say. So we measured this the dispersion relation on manganese difluoride, and we had 3 incident energies. And with this setup, if you have 3 incident energies, you have 15 constant energy planes that you measure. So you slice through this dispersion basically with 15 constant energy planes, and you can see in the data here on the color plots, you can see that you have this dot here, and it expands as you go up in energy transfer into a circle. And at high energy transfers, you see this focusing effect. So you see actually that the peak is narrower here on this side of the dispersion than on this side of the dispersion. And that is a well-known triple axis effect because your resolution function of a triple axis spectrometer is tilted in Q and omega. So on one side of the dispersion, you're focused, the dispersion and the resolution is parallel or pseudo-parallel, and on the other side, it's the opposite. So you can see this on a sample rotation scan. You can see that the signal to noise on one side of the dispersion is much higher than on the other. That is a well-known effect that you can take into account by designing your experiment. Then I'd like to measure, before I open up to some questions, I'd like to mention Bambus at PANDA. So this is not built yet, but it is to be built. It is funded, so it will happen as far as I know. And I like this design as well because it's similar to MultiFLEXX, but they use large analyzers, and they're taller, and they can be placed side by side in an alternating geometry where you alternate between scattering upwards and scattering downwards. And what that does is that it allows you to pack in more graphite without having gaps in a small scattering angle interval. And of course, that's perfect for magnetism where you prefer to stay at low Q. So that's one of the advantages. And the other of the advantages is that you have more flexibility in how you scan now, because this is a compact setup, so you can scan as the 2 theta parameter as well as the sample rotation. And that allows you a bit more flexibility in where you measure in Q. So there are some advantages with this MultiFLEXX and Bambus concept. I think Thales at the ILL is thinking about building one version of this with silicon. I don't know how far that is coming along. But the pros of this setup is that the angular resolution of the backend is good. You can use these low EFs if you wanted to map near the elastic line. You can have the choice of good elastic line resolution because you have this 2.5 MeV analyzer. The constant delta E maps can all be used. It's a relatively low cost because you have these small analyzers and simple tubes, and it's a transportable setup. The data is not so easy to normalize because the geometry of each channel, of each final energy channel is actually quite different. So that needs a little bit of thought. Open geometries, they have a cost and energy resolution, as we saw, a large acceptance angle, and they are spurious if you don't have a filter and radial collimation. And of course, a filter is expensive now because you have to cover quite a wide scattering angle interval with your filter. And this design works poorly above 5 MeV final energy, at least if you use pyritic graphite, because of these parasitic reflections. So I think this might be a good time to ask if there's any questions so far.
Thanks, Rasmus, until here. So, I mean, if I look at the list of attendees, then I would say that's who is who in neutron spectroscopy. So I think everything seems to be clear. And I'm also looking forward that you get to CAMEA and BIFROST. So I think we continue here.
Okay.
And then have the questions at the end.
All right. All right. Okay. So now I'd like to move on to discuss the CAMEA principle that Christoph is looking forward to, and it's continuous angle multiplexing energy spectrometer. Energy analysis actually is the name. That was a mistake on my part. The ideal here is that you multiplex an energy like we've seen on the MultiFLEXX, but you have a continuous in principle analyzer coverage, where you have these curved in principle analyzers that curve around in scattering angle, and then they scatter, of course, upwards to a detection plane where you can detect neutrons in this whole plane. And by detecting where on this curve that you measure your neutron, you can basically deduce which scattering angle you're talking about, basically, because of the finite mosaicity. A neutron can't scatter from here to here because of the mosaicity. So you use the mosaicity to get some scattering angle resolution instead of using channels. So that's, of course, a very good idea, but it's very hard to realize in practice. So I'm just going to move on to talk about what they did at PSI. So at PSI and the PSI CAMEA, we were utilizing this principle by building channels like we've done on the other machines. But the channels are a little bit special in one regard, because they focus in the vertical, so they scatter vertically upwards, and they focus in the Bragg plane, but azimuthally they're flat, basically. So that allows you to cover the whole continuous scattering angle interval, I think 60 degrees in 2 settings. But the thing with this is that you have the incoming beam here, and then you have a scattering angle here. And since the analyzers are flat, the scattered beam keeps expanding as it moves towards the detector, and then it becomes wider and wider perpendicular to the Bragg plane. And if you put in your 1D tubes here with precision sensitivity in that direction here, you can do this trick where the precision measurement here actually translate to a scattering angle on your analyzers. And that gives you a good scattering angle resolution, and it allows you to put more graphite close to the sample position. So Marty, he did the calculations of the resolution, and this is just this geometry flipped into a plane on a piece of paper. And there are 3 effects that goes in, a lot of effects that goes in and influence the resolution, but it's mainly the sample dimensions, the detector resolution, and the mosaicity. All of those comes into play, defining your scattering angle resolution. And of course, the length between sample and analyzer and detector. So of course, what the take-home message here is that you need to control your mosaicity quite strictly in order to have a uniform scattering angle resolution on your spectrometer. So that is one of the requirements for building something like this. But the really cool thing about this design is that you can do your persistent sensitivity trick with the mosaicity in the azimuthal direction, but you can also do it in the Bragg plane direction. You can actually also use persistent sensitivity to improve the energy resolution of your backend. And that you can do if you have a very small sample and you have a very small detector, so to speak. You have a well-defined Bragg angle now, regardless of what your mosaicity is of your analyzers. And that persistent sensitivity in the Bragg here, on the detector plane here, allows you to kind of select out to multiplex an energy, basically, to use a broad mosaicity to do these narrow multiplexing channels in the mosaicity distribution or the scattering distribution of the analyzer. And that is a way of improving the resolution of the backend, basically. You can see the resolution of these peaks here. The full width half maximum is very small at 5 MeV in the simulation. So that allows you to gain resolution on your backend without actually putting in collimators and sacrificing flux as a starting point or intensity of flux. So that's a very nice setup. So since you need to do persistent sensitivity both in the azimuthal direction but also in the radial direction, you have a lot of persistent sensitivity going on in your instrument. And what they chose at PSI is that they chose to build this radial ensemble 2 layers of 1D detector tubes, basically. So they cover this whole area, and that allows them full flexibility on how to multiplex, basically. So that's what they did. They put all this in a vacuum tank, and they also recognized the need for both filter and radial collimation. So they were clever enough to integrate it into one construction that they put inside the vacuum housing. And this is basically just a radial collimator where you put beryllium wedges in between the collimating lamellars, and then you cool the whole thing down. So that serves both purposes, and it's compact. And of course, the reason why you have to do this in a compact way is because you need to get the analyzers close to the sample to maximize the spatial angle coverage, because otherwise you start spending money on graphite. And this is a picture of the beautiful machine at the PSI. CAMEA has been built. It is in commissioning, but we know it works, and that's very positive, especially for BIFROST. The pros are that the scattering angle resolution of the back end is good because of this mosaicity trick. The good triple axis resolution is retained here. You don't sacrifice resolution when you build a setup like this. And if you utilize the prismatic backend, the primary spectrometer will end up dominating the energy resolution, and that makes it more likely to be able to add, to compare data from different EFs, basically, which they can easily do. Massive gains in efficiency you have there, and it's a compressed for magnet, so it's also a setup that works in one scattering plane. I don't know if this is really a con, actually, it's just a wild guess, but I think normalization is sometimes tricky because your angular geometry is something you need to take into account when you normalize. There's the volume of the resolution function, basically. And it's relatively expensive with the vacuum tanks and the 1D detector tubes. In their setup, the low EFs, the 2.5 MeV EFs, is not accessible. And you can merely you cannot match the back end resolution because your front end is a triple axis front end, and that has the resolution of a normal triple axis, and that would dominate the resolution of the entire measurement. But CAMEA is another example of a dedicated multiplexing build. It's well designed and it's well funded, and it works rather well. So there's a good example. I think they made this. I think they recorded this data 1 month after they started the hot commissioning. And it's a 2,800-year-old artificial pigment, and it's a spin-half system, and it's relevant for both Einstein physics, condensation physics. But in zero field, they measured these nice spin waves. And as you can see here, this plot is made out of data from different EFs, basically. But you can see the simulation is quite nicely reproduced, both the dispersion relation, but also the intensity is actually quite nicely agreeing with the simulation. So that is a very positive thing, of course, because that just demonstrates the power of using this principle. So now I'm going to move on to the final instrument to discuss, and that's my own, or our own, and that's BIFROST at the ESS. So it's easy to explain BIFROST now because I already explained the backend. It's basically exactly the same type of backend as on CAMEA, but what we have chosen to stagger our analyzers a little bit in order to make space for detector tube triplets. So we have 1D detector tubes arranged in series in shielding boxes here, and that provides us the 2D position sensitivity that we need, basically. The front end is not a TAS front end, of course. It's a time of flight front end, an indirect time of flight front end, but we have some slits here that can adjust the incoming divergence. So the way it works is that, you all know, or most of you know, the ESS, the classical ESS plot here, where you see the long pulse source. The pulse has a lot of intensity in it, and if you can use the full pulse for spectroscopy, you end up getting a lot of intensity. And because BIFROST is such a long instrument, we're able to get a decent energy resolution, even using the full pulse. The relative wavelength resolution is usable at 162 meters. But we can also use this pulse shaping chopper to chop up the pulse and increase the energy resolution of the front end. And that becomes a powerful feature now, which I'll explain in a moment. But on BIFROST, we of course have, because it's an indirect geometry front end, we don't have a monochromatic beam. We have a polychromatic beam with a wavelength band of 1.7 angstroms. And that in total yields a flux 2 megawatts accelerator power. We end up with a flux of 6 × 10⁹ neutrons per second per square centimeter. So this flexibility of the front-end resolution is quite powerful now, because we play the same trick as they do on CAMEA. So we do the same, we have the same position sensitivity in the Bragg plane by having these detector tubes. And each of these tubes, they select out a slightly different energy with a very narrow full width half maximum. So if you can match that 50 micro eV width with your primary spectrometer, you can gain a very large, a very good energy resolution of your overall measurement. And of course, at 2.8 millisecond pulse width, we don't match that resolution. We just go for flux. But if you chop the pulse down to 0.1 millisecond, for instance, you get a very good energy resolution of your entire measurement, even in the deep inelastic or a relatively deep inelastic. And the flux is still reasonable, you know, even if we chop down, we just lose a factor of 30 in flux, but that's still very much usable for spectroscopy. So that's the strength of this design. So the pros of something like BIFROST is that the overall scattering resolution, angle resolution is still good. The energy resolution can be very good, even far from the elastic line, and the polychromatic flux is very large. It's optimized for small samples and extreme environments, so it's optimized for something like pressure cells and tight high field magnets. I hope there will be a low background. It's not something I can say now because the instrument doesn't exist, but I really hope that because we're so far from the source, and because we're very aggressively shielding it, I hope the background will be low. In case of relaxed resolution, you might be able to add different KFs. So if you want to add data sets, you might be able to do that on BIFROST, because you probe a similar energy transfer Q value on all the analyzers, basically, on most of them. So the cons are that it's not designed for large samples. You can't use a large sample of this instrument, not if you want to go for high resolution. The very large energy transfer coverage that we have using this polychromatic beam is not always an advantage. If you don't need that bandwidth, you're just wasting the neutrons, basically. But the 1.7 angstrom is kind of a prerequisite for the whole measurement, the bandwidth. And we're limited to one scattering plane. So if you have a strong scatterer and you want to measure a four-dimensional data set, this is not the instrument to do it on. A time-of-flight instrument like C-SPEC will likely be a better performer. So I have reached the concluding remarks. The multiplexing, it works, and on a triple axis, it can really boost the performance and open up a niche. A lot of these backend geometries, they have a little coarser energy resolution than standard TAS, and they need careful designs to avoid crosstalk and background. But the simple setups, they are perfect optional setups on a TAS. So if you want mapping capabilities on TAS on a triple axis, these are a good ways of doing it. The more complex systems like CAMEA, they perform better and they are more flexible, but they are also more expensive. So they should be dedicated instruments, but that's also worth it, I would say. It's really a nice instrument, CAMEA. Open transparent multiplexing, what we did is that needs both radial collimation and beryllium filter. And the final energy needs to be below 5 MeV. And if you utilize a wide PG mosaicity, you can use that for multiplexing in both scattering angle and energy. And that's a very elegant way of multiplexing as far as I'm concerned. And this prismatic analyzer concept, the multiplexing and energy, that's very powerful in combination with an indirect time-of-flight front end like BIFROST. So if anyone else has a long pulsed, high-intensity source, this might be a good instrument to put on there. And that's it. Thanks a lot for your attention.
Thank you very much, Rasmus, for this nice presentation of novel multiplexing backends. And as you said, CAMEA is running already. And before the questions, I invite you already and make a little advertisement for our instrument. And you can apply for beam time in May at the next call for CAMEA if you want to see it in action. But now I don't see any questions from the attendees. Please use either the question and answer or the raise hand buttons if you have questions. If not, in the meantime, I would like to add that there is another concept ILL is working on, which is with bent silicon as analyzers. And that looks also very, very promising in terms of also signal to noise. Tanya Lucia raises her hand. Let me see. Then I can, wait a second. Tanya Lucia, I allowed to talk now, Dania? Or Diana, sorry.
Yes, hello. Sorry, I was about to write here. Okay, yes, I have a question. Is there any plan for BIFROST to set like, or to use like artificial intelligence to set up or to optimize scans?
To optimize scans?
Yes.
That's a good question. No, there's no plans. The short answer is no. The longer answer is that we will have a dedicated data scientist to work out how to best utilize BIFROST and for instance also CSpec. And he will also look into to artificial intelligence in a way. But I think that would be more on the data analysis side because our measurement is relatively fixed. We basically have a fixed geometry on the back end, and what we end up we also do these two setting measurements, and then what we end up adjusting is basically just the opening time of the pulse chamber chopper. So it's the measurement will be relatively straightforward, I hope.
Okay.
Let me add to this. There was the highlight just recently on the ILL, and Martin Böhm and co-workers used concepts of artificial intelligence to do exactly this on TALES.
Yeah, okay.
You find it in the most recent newsletter.
I saw that actually, yes. I think an instrument like Bambus would be good for that because you have a lot of flexibility in where to position your analyzer arrangements.
Then there is one question by Thomas Goodpellet, and he asks, what do you consider as a large sample at BIFROST?
So the guide system is optimized for 1 square centimeter beam spot, basically. So anything larger than that, then your prismatic analyzer concept that falls through, and you don't really gain intensity. So above 1 square centimeter in cross section, then it's too large. But that's still quite large.
Let me see if there's another question. Don't see any. Then I ask when you mentioned it already, maybe the amazing thing is also that the energy and Q resolution is comparable or sometimes even better than with the triple axis, which is due to distance collimations most likely. But can you quantify this a little for the audience? What did you expect there?
Yes. If you use this, for instance, on BIFROST, if you have these analyzers and use the mosaicity for multiplexing and scattering angle, the angular resolution is something like 0.6 degrees for the analyzers close to the sample and 0.8 degrees for the analyzers far away. So 0.6 degrees, and that is a couple of centimeters, 2 or 3 centimeters analyzer width, 1 meter from the sample, something like that. So that's relatively good. And if you can match it on your front end, then you will have a good Q resolution overall.
Then Jörg Voigt asks about the pulse shaping chopper, if it's a single disc.
Double disc. So it's a co-rotating double disc chopper with an opening of 170 degrees. So they rotate, and then you can adjust the opening, the effective opening angle of the chopper ensemble, as well as the frequency. So you of course maximize the frequency, and then we adjust the opening angle. So I think 196 hertz is what we, or 94 hertz, or 96 hertz, and then 210 hertz. That's the region we're aiming for a maximum speed.
Okay, then there is another question by Diana. Diana, I think you can, let me just see. Diana, if the mic is open, should still be open.
Yes.
Yeah, so you can ask your question, yeah.
Okay, thank you. So if you want to do a line width study, that usually you would use the triple axis spectrometer for that. But now if you're at ESS, which kind of instrument will be more suitable for that? Still like a classical time of flight, or you think BIFROST will give you an advantage?
Oh, that's a good question. I think if you have an isotropic scatterer, I think you should go to a time of flight machine. So if you can just add up everything in the vertical. But if you're interested in something anisotropic, if you're interested in one scattering plane, I think BIFROST could be useful because you can go to something like 20 micro EV resolution, and that's coarser than on an instrument like Miracles, but then the flux is also higher.
Okay, thanks.
And there's another question by Peter Link, and Peter, I will allow you to talk now. Peter, I thought I allow you to talk. Ask you unmute. Steph, can you help me in the back?
I think it should be on my micro now.
Yeah, we can hear you now, Peter.
Okay, hi all. Hi Rasmus, hi Christoph. During your talk, you passed by this the topic of background. BIFROST CAMEA are, let me say, kind of a very open designed backends, and so when you did this, you showed this slide with the union concept for background issues from the sample environment. What is your expectation for the BIFROST backend in this for this topic?
Yeah, I expect and hope that the background problems on BIFROST will be very small because of the distance between the source and the sample. It's 162 meters. So an extra 10, 20 centimeters on the front end doesn't really matter that much. So it should compress the spurious background from a magnet into the elastic line. That is the expectation. Yeah, and on an instrument like CAMEA, it is an open geometry. That's true, yes. But the detectors, if you integrate over a very limited area on your detector plane, so there is a bit of a closure of the geometry there. So I hope there won't be a large background problem on an instrument like CAMEA either.
Okay, thanks for the comment.
Yeah, I think I don't see any more further questions. Then let me thank you again, Rasmus, for this talk, and the audience for attending. And then despite the difficult times we are in, I hope you will nevertheless have a nice Advent and Christmas season. Already now, happy Christmas. And then hope to see most of you again next year when we continue this webinar. Okay, bye-bye now.
Thanks, bye-bye.
Tschüss.
Bye-bye.